like to first begin by thanking the main initiator of this lecture series, Professor Sushanta Dattagupta, for making this possible, and also, of course, the director of the institute, Professor Saurabh, Professor A.D. Sharma, and also Professor Panigrahi for giving such an eloquent introduction. So it feels very good to be back here. Let me tell you the genesis of this lecture series. Professor Sushanta Dattagupta, of course, said, he likes me, so he said, why don't you come and give a set of lectures, what to speak on. Then he said, well, I run this Center for Advanced Materials, and I have also asked Professor D.D. Sharma to come and lecture, and would you be able to combine your lectures with D.D. Sharma? And that's a very complicated project, because you have heard about orbitals in the morning, and my friend lives in what is called a DB orbital, which can never be localized. So then somehow we had to surmount this barrier, when to find time, etc., and then to decide on what we should talk on. Now it's very nicely done that I get in over the telephone with Didi, and he's going to stay here for only 1.5 days. And so in 1.5 days he's going to pack in things like the Hubbard model, how to extract parameters from the Hubbard Q, the Hubbard transfer integral, the exchange energy, and all this sort of things. So, okay, good. Then maybe I will try to help the students to set the basic foundation of the Hubbard model, which is what is called the tight binding model. So that's how the whole thing started, and then suddenly both Shayan and I thought that it would be wonderful to get Professor Saurabh, because see, the way we are complementing is, first you saw the logo that Sushanta Dattagupta has created. Dattagupta is sandwiched between Pal and Sharma. So I'm the only physicist in this group of distinguished speakers, my two distinguished speakers, and I'm sandwiched between them. I never roomed with them in IIT Kanpur. So that's how the complementarity starts. Now the complementarity actually goes further than that. Though Professor Pal said that the solid-state wallahs will talk about lattices and infinite space, etc., and I will talk about atoms, molecules, individual entities, actually we will also start from atoms and molecules, because again, coming to Shayan's center, Shayan deals with advanced materials. So what are the advanced materials today? They are nanomaterials. They are basic electronic materials. And so, today, like Richard Feynman said, there's plenty of room at the bottom. We have this bottom-up approach. We try to create a lattice or a solid from the atom picture. So that's how we complement. And then there are many other ways of complementarity. Professor D.D. Sharma will talk about experiments very important, called electron spectroscopy and photoelectron spectroscopy, and Professor Pal already introduced the photoelectric effect. And so photoelectron spectroscopy, all kinds of spectroscopies are very useful tools to understand today's materials. And so what I would like to do is also to set up the language for spectroscopy. At this stage, it is interesting, when Professor Pal was taking a census of the students, and they are mostly physicists, I want to tell you that in the area of materials, in the area of many other things like mesoscopic systems, nanosystems, which are systems of great technological importance today, quantum mechanics is the basic language. You already saw that in this beautiful overview that Professor Pal gave, that you have to have quantum mechanics. And though in many other places, chemistry faculties may not admit it, there is more quantum mechanics today in chemistry than even in physics. I dare say that because in physics, if you look at it, many physicists do nonlinear dynamics, they do gravitational structures, chaos theory, etc., the buzzwords, but there is hardly any quantum mechanics. But you cannot do chemistry without quantum mechanics. So historically also, as has been said before, that you saw the black body radiation of Planck, photoelectric effect, Planck of 1900, Einstein photoelectric effect, black body radiation theory 1905, Niels Bohr 1930, the atomic spectra, and then you saw the uncertainty principle of Heisenberg in 1926, the Schrödinger equation 1955. We didn't hear much about Dirac, but we will have it in the context of graphene. This is 1930 when relativity was brought in. But interestingly, there are three individuals, and one name has already surfaced, used quantum mechanics, then evolving quantum mechanics in the early 1930s to apply quantum mechanics to problems of great practical interest. One is Slater. You heard about it, how it is the Slater determinant from the exclusion principle and the Fermi antisymmetry of the wave functions of two or more fermions, such as the electrons. Then the other person is Van Vleck, who wrote this classic book on electric and magnetic susceptibilities. So magnetism is something that Van Vleck applied the new quantum mechanics into, and then Linus Pauling. Pauling was actually in Göttingen with Max Born. He learned quantum mechanics and he wrote this, this book called The Nature of the Chemical Bond. So in all these things, quantum mechanics is extremely, extremely important. So the way we're going to start is the way Professor Pauling introduced, that what happens in a single atom. And from there, we would like to get into what is called the tight binding model. Professor Sharma will tell you a little more about where the tight binding model finds more applications. So this is an approximation, right? It's an approximation of a lattice in which you have the nuclei at the lattice sites. The nuclei, since they are much heavier than the electrons, they move very little compared to the electrons. It's something called the Born-Oppenheimer. So we ignore the nuclei, but we have to contend with this very strong Coulomb interaction between the electrons and the nuclei. You're dealing with many electron systems. So Professor Paul will tell you how to handle this many electron wave function. It's a very complicated problem. A, the Coulomb interaction is a very long range interaction, so you have problems of boundary conditions, etc. So you have to simplify the problem. One of the simplifications is what mentioned already, is a Kohn-Sham, Kohn-Wernberg theory, density functional theories, etc. Incidentally, how physics, chemistry, they're all merging together can also be seen from the fact that Walter Kohn is a physicist, but he got a Nobel Prize in chemistry. And it's not just physics and chemistry, even in biology, when our lone biology colleague has disappeared, that even electron transfer reactions, for instance, in hemoglobin is a chemical reaction, but uses quantum mechanics. Routinely you use NMR, proton magnetic resonance in biological systems because, of course, you have water in your body, in your blood you have iron. And so whenever you are doing water, studying protons and you NMR, so you need quantum mechanics in biology, you need quantum mechanics everywhere. Even in earth science, I used to give this example of where interdisciplinary is very important, is that if you have a tsunami or a big earthquake, the stress waves are so strong that you actually break chemical bonds. When you break chemical bonds, you change the nature of the soil also. The soil chemistry changes, agriculture changes. So therefore, today we cannot afford to live in our own cocoon of one discipline. And the IICR system is all about going into these interdisciplinary areas. So the tight binding model is a very simple way of looking at a solid by saying, how did I form a solid? Well, you say that I start from a single atom and I bring another atom together. I keep on doing this and then I form a lattice. So what happens to a single atom? So Professor Pal already showed that if you have, let's say, hydrogen-like atom, okay, its wave function is a symmetric wave function, and in fact, you can write it as psi of rho, if you use cylindrical coordinates, has an exponential of minus rho times what is called the Bohr radius. Okay? So it's not really a Gaussian, it actually falls off exponentially. Alright? Now, then I have another atom, let's say, and that also has its wave function. Okay? So you call it psi left and it's psi r. Alright? Now this is when the two atoms are far apart. So I say a simple example of a hydrogen atom, you have one proton and one electron. Now when I bring them together and a little closer, then what will happen is the wave functions will start overlapping. Right? We have composite wave functions. So how to describe this composite wave function? Now quantum mechanics says, so now we see what happens is, when the wave functions overlap, you have lost the identity of an electron. You cannot say which electron is where. Because in quantum mechanics, all we know is the electron density. And the electron density, as was also mentioned in the morning, is given by the mod psi squared. So we only talk about electron density now, without reference to which electron is where. So now I bring them together, and then we have something called the superposition principle. Which says that I can have two possible combinations, psi L plus psi r, or psi L minus psi r. I'm not using normalizations, to form two linear combinations which are equally admissible in quantum mechanics. Okay? So the question now is that how would psi L plus psi r look like, and how would psi L minus psi r look like? So when you combine the two wave functions, you get a picture like this. So if you look at psi L plus psi r, then you have what is a symmetric wave function, right? Because I have just added these two. So I call this psi s. Actually, you need a 1 by root 2, the same root 2 that appeared in the past lecture. And then when I subtract psi L minus psi r, in the place of the second atom, I get a negative wave function. So the wave function then starts looking like this. So let me draw it a little more carefully. It goes like this. And now this is psi symmetric, and psi anti-symmetric is 1 over root 2 psi L minus psi r, and that will look like, see, at this point you have a large wave function because of this, but now as I go to the other side, I go to the negative side, and so I get something like this. So this is a symmetric function, this is an anti-symmetric function, right? In terms of the permutation operator or in terms of the parity operator. Now, physically what is happening is that you see the electron density is substantial at the center between the two atoms. Here the one and the second, first atom and second atom is substantial here, but it goes through a node, goes through a zero in the middle. So therefore, it means that because the Coulomb attraction between the proton and the electron density is substantially large at the midpoint for the symmetric wave function than in this case. So this state therefore is of lower in energy than this state, lower in energy, and this is higher in energy. A tiny amount though, and this is why this is called a bonding state, and this is called anti-bonding. So this is the basic idea of Pauli, okay, how bonding occurs by basically bringing in two atomic wave functions. Now, you might have seen similar pictures. Remember, Professor Paul said for, by the way, I also said, I didn't say that another place where Saurabh compliments us is that he will also talk about various numerical methods. You see, the way the science of materials evolves, you have theoretical studies, you have experimental studies, and you have computational studies. I mean, each of the three is equally important, and you have to have a combination of all three. So in a sense, we actually also combine like this. So this, though he said that, this is actually an exponential function, these are the lowest Hermite polynomials. You can also use Gaussian functions. So let me give you another example. Two positive charges here, and the electron is being attracted. Attracted means binding, okay? And it's shared by the two protons, okay? Okay? So therefore, therefore there is a lowering of the Coulomb energy. Yeah?
Yeah, because if I think about the charge density, the antisymmetric is at the center.
There is no charge.
No charge.
And this you already have so we can consider that undergoing a constructive interstellar experience.
Precisely. So you'll see that this kind of two-state ideas, I mean, he already introduced another way of two-state ideas in constructing a Slater determinant of 2 by 2. So these two-state ideas are very interesting and very important as building blocks. And we want to do simple things, right? And so we want to build a many electron wave function from a two-state model like this. But you can also do many complicated things with the two-state system, which we will try to indicate. So the other example that physicists might be familiar with is that what is called, I mean, you'll find this in a book called Merzbacher, Quantum Mechanics. It's a double oscillator model where you actually see representations of Gaussian wave functions. So imagine that you have two oscillators back to back. Okay, so all of you have seen harmonic oscillators, right, in your first course in quantum mechanics. Now you bring in another oscillator, and so the Hamiltonian that you can write down is half m omega squared x mod squared minus a squared. So at x equal to plus a and at x equal to minus a, you have 0 of the Hamiltonian. The energies go to 0. But at x equal to 0, this is